Welcome! Today, we're going to take a huge leap from the calculus you might remember, finding the area under a curve, and jump into the incredible world of multiple dimensions. We're going from the comfort of a simple line to the complexity of, say, a cloud. So how on earth do we even start to measure something so massive and, well, all over the place?
Really think about this for a second. A cloud isn't just a solid block, right? It's wispy over here, way denser over there. How could you possibly add all of that up? It seems kind of impossible, doesn't it? Well, this is the exact kind of problem that multivariable integrals were invented for. And by the end of this, you'll see exactly how it's done.
So, here's our roadmap for today. We're going to start with a quick refresher on what we already know. Then, we'll build up one dimension at a time, from finding simple area to calculating volume, and finally to measuring stuff inside that volume. And then we'll get to the most important part, why this isn't just abstract math, but an insanely powerful tool for understanding the world around us.
All right, let's ease into it. We're starting on familiar ground. Section 1, a quick recap of single-variable calculus. You remember this, right? The single integral. At its heart, it's really just a powerful method for summing things up. We slice the area under a curve into a bajillion super thin rectangles and then just add all their areas together to find the total. The key idea is just summing up tiny pieces. To make this all feel a bit more intuitive, let's use an analogy we can all get behind. Think of a single integral as just calculating the area of one perfect, flat slice of bread. The bottom is your x-axis, and the curvy top is, well, your curve. Pretty simple.
So a single integral finds an area by working over a one-dimensional line. But to get to the next level, we're going to need to find a volume by working over a two-dimensional area. And that right there, that's the big conceptual leap we're about to make together.
Okay, so let's build on that foundation. Welcome to Section 2. We are officially adding a dimension. We're moving from a line on a page to a flat surface, like a tabletop or a floor.
So back to our bread analogy. One slice is great, but what about the whole loaf? The top crust isn't a straight line, it's a whole curved surface. How in the world do we find the volume of the entire loaf of bread? And that's the big shift in thinking. We're not just calculating the area under a simple line anymore. Our new goal is to find the volume underneath an entire two-dimensional surface. We've literally gone from a flat drawing to a 3D object.
So what's the tool for this new job? Well, that brings us right to Section 3, the double integral.
A double integral basically does for volume what a single integral does for area. It's a method for summing stuff up, but this time it's over a whole two-dimensional region, like a square or a circle on the ground. It gives you the total volume between that floor and whatever curved ceiling is hanging above it.
So how does this thing work? It's actually really clever, and it builds on what we already know. First, you kind of freeze one direction and integrate along the other. That's just like finding the area of one of our thin slices of bread. Then, you take that answer and you integrate it along the second direction. That's like stacking up every single one of those slices to get the volume of the whole loaf.
So here's the absolute key takeaway. You can just think of a double integral as summing up the sums. First, you sum up tiny bits to get the area of one slice, and then you sum up all of those slices to get the total volume. It's a really elegant and powerful idea.
Okay, great. We can find the volume of a loaf of bread. But what if we want to know something about what's inside it? This brings us to our final, biggest leap into 3 dimensions.
Let's upgrade our analogy. This isn't just plain bread anymore. It's raisin bread. And the raisins are all clumped together in some spots and really spread out in others. The density is not uniform at all. A double integral gave us the volume, sure, but it can't tell us the total mass if the density is changing everywhere inside.
For a problem like this, we need the triple integral. This is our ultimate tool. It doesn't just work over a 2D area, it works through an entire 3D volume. It takes a function, like the density at every single point, and sums it all up over the entire region to get a total quantity, like mass.
And this is the huge difference. With a triple integral, we've moved beyond just measuring the size of a shape. We are now calculating a property, could be mass, could be temperature, could be charge, at every single point within a 3D object and then adding it all up. This is exactly how we solve our cloud problem from the very beginning.
Which brings us to our final and maybe most important section. Why does any of this matter outside of a math textbook? I mean, is this really just a super complicated way to think about bread in clouds? Oh, not even close. The applications are literally everywhere.
For example, engineers use these all the time to find the center of mass for something like an airplane, where all the materials are different weights and densities. Physicists use them to calculate the strength of an electric field all around a charged object. Meteorologists use them to model these incredibly complex pressure systems. Basically, anytime you have a quantity that changes over a region or a volume, these are the tools you gotta use.
So if there's one thing you take away from all this, let it be this. The real world is messy. Things are hardly ever uniform. Density, temperature, pressure, they all change from point to point. Multiple integrals are the mathematical language we use to describe and to precisely calculate things in this beautifully complex, non-uniform universe we live in.
You know, we've built this all the way up from a line to a surface to a volume. It kind of makes you wonder, doesn't it? What sort of properties could we even sum up over a four-dimensional space? What kinds of problems could we solve then? Definitely something to think about. Thanks for joining me.